Right, welcome back to the class. We were studying about heterocyclic compounds. So far, we studied about pyrrole, furan, thiophene. That was in Unit 3, and Unit 4, we studied so far pyrazole, imidazole, oxazole, thiazole, and in last class we studied about pyridine. So in today's class, let's go ahead and study about two compounds, quinoline and isoquinoline. Let's study about the quinoline first. As you can see the structure of quinoline here. Quinoline has got two rings, right? One is a benzene ring, the other one is a pyridine ring. So the benzene ring is fused with a pyridine ring, and it is fused at alpha and beta positions of pyridine. So let's check that here. Okay, this is the alpha position, alpha to the carbon atom, that is alpha to the nitrogen. This is alpha position, right? And if this is alpha, this is beta position to that nitrogen. This carbon is beta position. So the fusion of benzene and pyridine is at alpha beta position of pyridine, right? So it is named as quinoline because it is first obtained from quinine, and quinine is the alkaloid obtained from cinchona bark, right? That is where it is obtained from, and it is for the first time obtained from cinchona bark, from quinine. So it is named as quinoline, and it occurs in coal tar, bone oil, and angusta bark. This is another bark other than cinchona bark where you can get quinoline. Right, these cinchona bark or cinchona and angusta, these plants are in American countries and African countries. That's where you can get them. Right, let's go to the structure. Just like the other heterocyclic compounds, all of the quinoline atoms, they are sp2 hybridized. So it has got one nitrogen, right? One nitrogen, even that has got the sp2 hybridized orbitals. Means it has got two, each atom has got two, a total three sp2 hybridized orbitals, and there should be one unhybridized p orbitals. All of these unhybridized p orbitals, including that of nitrogen, they will have one electrons in each. Okay, so totally it will make 10 delocalized electrons, and because of this 10 delocalized electrons in Huckel rule, we can write this, we can put 2 in number 2 for n, and when you do that, so you will get a total of 10. So it satisfies that Huckel rule. 4n plus 2, it satisfies that rule where n is equals to 4. That's why we can call quinoline as a aromatic compound. And the one extra electron, the nitrogen has got one extra electron, then the carbon, the one extra electron will be in one of the sp2 hybridized orbitals, and that is what is shown here. Right, this is the lone pair of electron in one of the sp2 hybridized orbital. Right, other than that, the ring is flat. It is in cyclic form. It is flat. It has got those delocalized electrons, and it satisfies Huckel rule. That's why it is a aromatic compound. This is the resonance structure of quinoline, right? If you shift the um, if you shift the electrons from these pi bonds to the nitrogen, and if you keep following the charges and the shifting of the bonds because of the variation in the charges, you're going to get these seven structures. So these are all resonance structures of quinoline. Right, let's go to the synthesis. The first method of synthesis is a scrap synthesis. In this, what you're going to do is you're going to take aniline, mixing that with the glycerol, okay, um, in the presence of sulfuric acid and nitrobenzene. You will have to heat this reaction mixture. The result is quinoline. You are going to get the product quinoline with this reaction. Instead of this nitrobenzene, you can use arsenic pentoxide. And this reaction is a violent reaction. It's an exothermic reaction. You can reduce this violent reaction. I mean, you can reduce the severity of the reaction by using ferrous sulfate or boric acid. So ferrous sulfate and boric acid, they can make this reaction less violent. And let's go to the next method of preparation. It is Friedlander synthesis. It's a condensation reaction. You are taking orthoamino benzaldehyde. This is the aldehyde group, right? And this is benzaldehyde. The whole ring with the ring, it is benzaldehyde. And there is at ortho position there is a amino group, right? So it is orthoamino benzaldehyde. You have to mix that with the acetaldehyde. If there is acid group here or the carboxylic acid group, it will be acetic acid. But there is a aldehyde group here. This is the aldehyde group, and this is a acetaldehyde. You have to mix that, and it is a condensation reaction where you will get the water, right? Water molecules are removed, and you are going to get the product quinoline, and you have to provide alkaline medium. You have to provide the alkaline medium for this reaction. Alright, that is the second method of preparation. Next let's go for the properties. In physical properties, it is a colorless liquid with the boiling point 237 degrees centigrade. It has got a pyridine-like smell, right? It's miscible in most of the organic solvents like chloroform, ether, and alcohol. It dissolves in water only to the extent of 7% at room temperature. Okay. If you heat the mixture, it can dissolve to, you can get the more dissolution rate. Okay, it turns yellow on standing. It's not that stable. It can change the color from colorless to yellow upon standing at room temperature. Alright, next we'll study about chemical properties. First one is basic character. It's basic in nature. A slightly weaker base than pyridine. It's little weaker base than pyridine, and it reacts with acids to give the salts. These salts are sparingly soluble in water. Here's the reaction with the hydrochloric acid. The protonation reaction takes place. The proton is going to get attached to the nitrogen, right? So you're going to get this salt, quinolinium chloride. That is the salt you're going to get, right? Let's go to chemical reactions. In that, first one is electrophilic substitution reaction. In normal condition, you don't get the electrophilic substitution reaction. It is going to give the electrophilic substitution reaction only under vigorous conditions. So the substitution is going to take place at the C8 position, right, and C5 position. So what are the positions here? This is number 1, 2, right, number 3, number 4, right, number 5, this is number 6, this is number 7, and this is number 8. Right, while numbering you are not going this way, right, you are not going this way, you have to go this way, because there is a fusion here, there is fusion here, you are not going on fusion side, you have to go on the other side, other way around. Alright, now you observe one thing here, substitution is going to take place either on the pyridine ring or benzene ring. Whether pyridine or benzene is going to support electrophilic substitution reaction more. That is benzene ring. Benzene ring is going to support the electrophilic reaction more because benzene has got more electron cloud. What is the electrophile? Electrophile has got the positive charge. It is the Lewis acid, positive charge. And here, in here, this is more of negative. This is more of negative. This is of little, this ring is of little positive because there is electronegative nitrogen here, right? There is electronegative nitrogen here, more of electrons will be towards this nitrogen. That's why this will, the positivity of this will get exposed. That's why the electrophile is going to attack on benzene ring rather than the pyridine ring, right? So the substitution takes place at either at position 8 or position 5, and in the nitration, in the presence of oleum or fuming sulfuric acid, so you are going to get 8 and 5 nitroquinoline. First you are actually, this is substitution at position number 8 is going to be more or more faster than substitution at position number 5. Okay, so that is the electrophilic substitution reaction, that is the reaction of nitration as an example. Let's go to the sulfonation next. It is almost the same kind of reaction. You are taking oleum here, oleum you are taking because you need the fuming sulfuric acid, as we came across earlier, that it is going to give the substitution, electrophilic substitution reaction in vigorous condition. That's why we are taking oleum. Okay, you have to provide the heat. So your quinoline reacts with this sulfuric acid, and you are going to get 8 and 5 quinoline sulfonic acid. So the substitution at on benzene ring at 8th position and at 5th position. Alright, let's go to the next reaction. It is nucleophilic substitution reaction. Substitution takes place at position number 2. This time it takes place on the pyridine ring, right? It takes place at C2. If C2 position is blocked for any reason, if some other group is here, then it's going to take place at C4. 1, 2, 3, 4. Then it is going to take place at C4. That is here. Now, why the reaction is going to take place at I mean the attack is going to take place on the pyridine ring? As I told you earlier, this is little positive, and here it is negative, and this is completely negative. This ring is completely negative. Nucleophile Mu, right? It's negatively charged, and this nucleophile is going to attack on the pyridine ring. So as an example here, reaction with the sodamide at 100 degrees centigrade in the presence of liquid ammonia. In the presence of liquid ammonia, you're going to get the substitution at position number 2. So you're going to get 2 amino quinoline as the product pair. So that is a nucleophilic substitution reaction with the example reaction with the soda. So next we will see the same reaction but with the N-butyl lithium. So in case of N-butyl lithium, this is N-butyl group, and this is lithium. Lithium is partially positive charged, and N-butyl is partially negatively charged. So this is going to attack on here. This is the nucleophile. Right, nucleophile is going to attack on position number 2, so you're going to get 2 and butyl quinoline as the product. Alright, next is oxidation. Oxidation, you need the little drastic condition here using peracetic acid. You have peracetic acid here. Oxidation is going to take place. You are going to get quinoline and oxide. So the oxide, the oxygen, we are going to get substitute over here on the nitrogen of quinoline. So you're going to get quinoline and oxide. So if you further use the drastic condition, if you use further stronger oxidizing agent, if you use potassium permanganate, in basic condition, right, the benzene ring is going to open. This benzene ring is going to open here, and because of that you are going to get pyridine 2,3 dicarboxylic acid. The benzene ring is going to open, and the your pyridine ring is going to remain intact with the 2 carboxylic acids um, of portion 2 and 3. So the product is pyridine 2,3 dicarboxylic acid. It is also called as a quinolinic acid. Next, let us look at reduction. So two types of reduction you can carry out. This is a mild reduction. Okay, this is vigorous reduction. Let's see what will happen with the mild reduction. Partial hydrogenation is going to take place. You have to take tin, okay, and in acidic condition, so reduction is going to take place, right? Partial reduction is going to take place, so you are going to get only the pyridine ring is going to get saturated with the hydrogens. You are going to get 1, 2, 3, 4 tetrahydroquinoline. So if you take or if you pass a hydrogen on platinum, right, platinum as a catalyst at 140 degrees centigrade, so the ring, both the rings are going to get saturated, get hydrogenated. So in that case you are going to get a decahydroquinoline product. All 10 positions, right, all 10 positions are going to get hydrogenated, including the nitrogen position are going to get hydrogenated. So it is a decahydroquinone. Alright, next is reaction with the alkyl halide, right? So N-alkylation reaction is going to take place. So this is your alkyl methyl iodide. Methyl group is partially positively charged, and iodine is partially negatively charged because it is a electronegative atom. It is going to attract electrons towards it. That's why it is partially negatively charged. So because of this, this nucleophile is going to attack on the nitrogen here. So it is positively charged, and then nitrogen has got the lone pair of electrons, so it's going to attack on the nitrogen, and you're going to get N-methyl iodide as the product or the salt. Alright, next is the medicinal uses of quinoline. Quinoline nucleus is present in various types of medications, right? The first one, drugs used to prevent, it is the quinoline ring you can see in the drugs used to prevent, treat malaria. So the examples are cinchona alkaloids. In cinchona alkaloids, you have quinine and quinidine. These are the drugs used to treat and prevent malaria. They have got a quinoline ring in them, and then it is also there in chloroquine, and it is also there in hydroxychloroquine or SCQ. This drug is very popular now. It's used in the treatment of COVID-19, right? You have seen this, I mean, you have heard of this a lot nowadays, that hydroxychloroquine, which is actually manufactured in India from IPCA laboratories, is used in COVID-19. It is getting exported a lot. The thing is, this drug is used in COVID-19 as a last option drug. If no other drug that is not going to work, then they are going to use this medicine as a last option. It is used on trial and error basis because they use this medication in SARS, right? That's why they are using it here now. Um, if no other drug is going to work on COVID-19. It is also used as prophylaxis in COVID-19. It is given to health workers on a prophylactic basis. Even Indian government has recommended this drug to be used as a prophylactic in case of healthcare workers. And this hydroxychloroquine is prepared using scrap synthesis method, right? Let's go to the next compound. I mean, the next users. The quinoline ring you can see in quinolone antibiotics, right? So it is quinolone antibiotics. Quinolone antibiotics are ciprofloxacin, ofloxacin, and norfloxacin. You can see the quinol quinoline ring over here, right? It's these are the derivatives of ciprofloxacin, ofloxacin, and norfloxacin are the derivatives of quinoline ring, and these drugs are used in bacterial infections, especially in cases of skin, respiratory, and urinary tract infections. They are used a lot, right? Now it's used in they are used in typhoid fever, right, and other these conditions. All right. In case of hydroxychloroquine, I mean, on this, here's the structure, and this is the quinoline ring. It's upside down than what we are writing, right? Um, in here, if this R is replaced by H, if this R is H, then it is chloroquine. If this R is OH, if it is OH hydroxyl group, then it is hydroxychloroquine, right? So that completes your quinoline compound. Let's go to isoquinoline, the next compound. As the name says, iso, it's an isomer of a quinoline, right? Isomers, here they are isomers because they have same molecular formula but different structural formula, right? But the numbering is done as the same manner as quinoline. Numbering starts from this carbon, the carbon over here. So the nitrogen is at position number 2 in isoquinoline, right? So It's a heterocyclic compound with the benzene and pyridine. They are fused, but they are fused at beta and gamma position. So this is the nitrogen position here. This position, this carbon is alpha carbon, right? This carbon is beta carbon to that nitrogen, and this carbon is gamma carbon to that nitrogen. So the fusion is taking place at beta and gamma position, right? Beta and gamma carbons, right? This isoquinoline occurs in coal tar and bone oil. This ring is present in many of the alkaloids that we will see at the end, right, in medicinal uses. The structure of isoquinoline, it is same as that of quinoline, so it's a isomer of quinoline. So structure, everything is same here. Let's go to the synthesis. They can be synthesized from cinnamaldehyde. You have to do a condensation reaction using cinnamaldehyde. Here is the aldehyde group. This is, if this is COOH group, then it is cinnamic acid, right? And you have to react that with the hydroxyamine. This is the hydroxy group, this is the amine group, hydroxyamine, condensation reaction, removal of water, you're going to get oxime. This is the oxime group, okay. You're going to get cinnamaldehyde. The compound is cinnamaldehyde. It is very unstable. It gets rearranged to this compound. The difference between this and this, as you can see here, the carbon is attached to the carbon here, but in this case carbon is attached to the nitrogen, and here one more molecule of water is getting removed in the presence of a phosphorus pentoxide, and you are going to get isoquinoline because of the rearrangement and removal of water or the dehydration, right? So that is the first method of preparation. Let's go to the next method of preparation is Pischner-Neprarsky synthesis. So in this, so you're going to react 2-phenyl ethylamine. So this is the amine position. This is phenyl group. This is ethyl, right? 2-phenyl ethylamine. You're going to react that with the formyl chloride. If this is H, it is formaldehyde. You have chloride group there, so it is formyl chloride. So there will be dehydration, and you're going to get N formyl 2-phenyl ethylamine, right? And this is going to get rearranged to enol form. This is the keto form, right? This is the keto form, and this is the alcohol form, enol form, right? And from this enol form again, you're going to take out the water using phosphorus pentoxide, right? You have to use pyridine as a medium here, right? In here now oxidation is going to take place or hydration in the presence of palladium, right? Hydrogenation is going to take place in presence of palladium. Sorry, the dehydrogenation is going to take place here, and you're going to get isoquinoline as the product. So this is the second method of preparation. So next we'll go to the properties, physical properties. It is a colorless solid. So it has got the melting point to 26 degrees centigrade. It has also got the boiling point. It has got low melting point. It has also got the boiling point at around 234 degrees centigrade. It has got benzaldehyde like smell. So what is the smell of benzaldehyde? It gives the almond like smell. So it has got the almond like smell. It is sparingly soluble in water. and it's soluble in organic solvents like alcohol, ether, and chloroform. It turns yellow on normal storage. It is actually colorless solid, but it can turn to yellow color upon normal condition. Normal condition in the sense at room temperature. At chemical properties, it's a stronger base than pyridine. It forms a stable salt with the acid like other heterocyclic compounds. Right, next we'll go for the chemical reactions in chemical properties. First one is electrophilic substitution reaction. Reactions are similar to its counterpart quinoline, right? It's going to give substitution at position 8 and 5, just like quinoline. Substitution is going to take place on the benzene ring, not the other ring, not the pyridine ring. So as you can see here, in presence of sulfuric acid, uh, nitric acid is going to react and giving 8 and 5 nitro isoquinoline product. So in presence of sulfuric acid with the heat, it's going to give isoquinoline only 5 sulfonic acid product. Right, next is oxidation with the alkaline potassium permanganate. It can give two kinds of product. The ring separation is going to take place here. So you can get phthalic acid and pyridine 3,4 dicarboxylic acid as the products. So next is reduction. In case of reduction, it's going to get hydrogenated. The in case of tin and combination of tin and hydrochloric acid, which is going to produce your hydrogen, it's going to get partially hydrogenated. So you're going to get 1, 2, 3, 4 tetrahydro isoquinoline as the product. So in case of reaction with the alkyl halide, that is methyl iodide, the nitrogen is going to go for alkylation. So an alkylation is going to take place, and you're going to get N-methyl isoquinoline iodide as the salt. Right, let's go to the next one. So we are going to see about medicinal uses. So it's widely distributed in the form of alkaloids. Right, the two alkaloids we are going to see here, or alkaloidal products we are going to see here. First one is papaverine. Papaverine structure, or the papaverine product you are going to see in opium or poppy seeds. The poppy seeds will contain opium alkaloids like morphine, codeine. Okay, morphine, codeine, they are narcotic substances or narcotic medicines used to relieve pain. So it is used only in cases of severe pain because it is addictive product, so it can cause dependency. Okay, the people can abuse this drug, so that's why it is used only in case of severe pain. Only in case of severe pain, right? It's not used in regular pain or the mild pain. Here you can see the papaverine structure. Right, here is your isoquinoline ring. Right, let's look about the second product, that is amethine. Amethine you can find in ipecac root, and this amethine product is used in case of amoebiasis. Okay, it is an anti-protozoal product, so you can use this in amoebiasis or amoebic dysentery. It is also used in case of or to produce in or the induce vomiting. So if by accident, if somebody ingests some poisonous substances or some object, so what you can do is you can give uh, amity or the extract of ipecac root to induce vomiting so that the object or the poisonous substance can come out. So you can do this, you can induce vomiting only, of course, in case of a poisonous substances, so only at the beginning, right? So you have to do this before it can go into the system. So it is also used as a vomiting substance. So this is the use, another use of isoquinoline. So this